All right, well, in this section, we're going to be looking at the chlorination of other alkanes that have more than one type of hydrogen. And in doing this, we're going to be interested in the ratio of how much of each of the products that we get. So, for example, propane has two different types of hydrogens. So there's the hydrogens that are on the end carbons, and then there's the two hydrogens that are on the middle carbon. So that means we get two different products. Now, if you were looking at just how many hydrogens there are that are available to be abstracted, we've got 6 of the hydrogens on the end, and we've only got 2 of the hydrogens on that secondary carbon. So you might think that we would get a 6:2 or a 3:1 ratio of the 1-chloropropane to the 2-chloropropane. But that's actually not what we get. We get about a 1:1 ratio. So even though there's fewer of these secondary hydrogens, we get a disproportionately large amount of chlorination on that carbon. So we want to figure out why that is. Well, the rationale for this can be explained by looking at the bond strength. All right, so we can compare the rate of the reaction with a secondary carbon-hydrogen bond versus a primary carbon-hydrogen bond, and we'll see that it's faster. And the reason that it's faster is that the carbon-hydrogen bonds, the substituted carbon-hydrogen bonds, are weaker than the less substituted carbon-hydrogen bonds. So if we look at methyl, you recall methyl is got 4 hydrogens on it. It is going to go slower because that bond is stronger, whereas these bonds are going to go faster because those bonds are weaker. So when chlorine reacts with alkanes, the more substituted carbon hydrogens are disproportionately favored to react. But it's not a very dramatic difference, it's just a little bit different. Right? Instead of getting a 3:1 ratio with the propane, we got a 1:1 ratio. So here is where we want to look at chlorination versus bromination. Now, before you start this section, I want you to pause the video and go on Google and search the Hammond Postulate. So go search that and read what the Hammond Postulate is. All right, now that you've done that, we're going to keep the Hammond Postulate in mind. We're going to keep the Hammond Postulate in mind while we're looking at this. So let's look at the difference between chlorination and bromination of alkanes. Chlorination goes faster than bromination. So if you're just trying to get the reaction done fast, chlorination is definitely a faster pathway. Bromination, however, is much more selective for more substituted carbon-hydrogen bonds than the chlorination. To illustrate how much more selective, we're going to go back to propane, the one we looked at a few minutes ago with chlorine. As you recall, we have a 6:2 or a 3:1 ratio of hydrogens for the primary hydrogens to the secondary hydrogens, but we only had a 1:1 ratio as far as the products. So it was a little bit more selective for the carbon hydrogens, or for the secondary hydrogens than the first primary hydrogens. But when we look at bromination, we'll see that selectivity goes way up. And in fact, with a 99:1 ratio, we're looking at almost 100%. I mean, this you can separate that out pretty easily. From your secondary bromination product. So bromination is slower, but it's more selective. So we want to answer, well, why is it slower and why is it more selective? And it turns out the Hammond postulate is related. So we're going to look at the first step of the bromination propagation. We did this with chlorine a little back in the previous section. We looked at this. And so if we look at the difference between chlorination and bromination, we look at that first propagation step, we'll see that the abstraction of the hydrogen, the carbon-hydrogen bond with the bromine radical is endothermic in that first step. So here's the first step, and if we look at propane again and we abstract the primary carbon-hydrogen bond, that reaction is going to be endothermic by 42 kilojoules per mole. If we look at the secondary carbon-hydrogen, we'll see that that one's going to be endothermic by 29 kilojoules per mole. And it's this endothermic reaction that gives us our selectivity. You may recall when we were doing this with the chlorine, it was those were both exothermic. All right, so so this is just saying that the delta H for the first step of our first propagation step, that is it's a little bit less endothermic for secondary than it is for the primary, but they're both definitely endothermic steps. So let's look at the energy diagram for bromination in its rate determining step. So we're just looking at the first step, and if you go back and look at number 55, the one we just did at the end of the last video, if you go back and look at that one, you'll see this first step, it's endothermic, and it looks something like this. Now, we're not drawing the second step. We're not concerned with that right now. We're only concerned with our rate determining step, our first step. All right, so it is endothermic, and this is where the Hammond postulate comes in. Do you remember, you just went and looked it up? Hopefully you did. If you didn't, stop now and go look it up. All right, so when you looked it up, you'll see that the Hammond postulate tells us that the transition state for a step more closely resembles the thing it's closer in energy to. So because this is endothermic, it more closely resembles this product than it does the reactants. In an exothermic step, it's the other way around, and we'll look at an example of that here in just a moment. So when we look at a comparison of abstracting a primary hydrogen, which is this red line, versus a secondary hydrogen, which is the blue line, and creating these different energy intermediates, the radical intermediates, we'll see that those will disproportionately affect the energy of our transition state, which in turn will affect the activation energy. And the larger that activation energy is, the slower the reaction goes. So this one with a higher transition state energy is going to go slower than the one with a lower transition state energy. This is like one of my favorite examples of the Hammond postulate, and I love the Hammond postulate. It's such a cool tool to use when you're talking about reactions and understanding intermediates or transition states, that is. All right, let's go back and look at the first chlorination propagation step, and we're going to compare it to what happened with bromine. So the abstraction of the hydrogen on the carbon-hydrogen bond with the chlorine radical, that is exothermic. Remember, for bromination, it's endothermic, and here it is exothermic. So for a primary, it's negative 21 kilojoules per mole exothermic, and for secondary, it's negative 34. All right. Since the chlorination is an exothermic rate determining step, that means that the transition state is going to more closely resemble the starting material. And as a consequence, the relative stability of the two radicals is less important. And let me show you that on a picture. So we're going to go to the next page and look at the energy diagram. And so again, because it's exothermic, this transition state is going to more closely resemble the reactants than it does the products of that step. So the Hammond postulate tells us that again, the transition state more closely resembles the reactant in this particular step. All right, so we're going to look at number 33. And switch over here. All right, so number 33, what is the major monobromination product for each by heating it with Br2? So really what we're looking at is with bromination, we just need to find the most substituted carbon-hydrogen bond. And tertiary is going to win out over primary, over secondary, and secondary will win out over primary. So if we look here, our most substituted carbon hydrogen here is going to be this one. It's a tertiary hydrogen. So that means we will get substitution at that tertiary hydrogen. So we'll just draw that. All right, and so we will get that as our product. All right, on this one, it's pretty easy because that one clearly is the most substituted. So we have a tertiary hydrogen there. And then there's our methyl. And then finally on this one, we don't have any tertiary. We've got primaries here and there, and we've got a secondary. This one's quaternary, so there's no hydrogens on there, so we can't get substitution there. But we can get it on that secondary, so we will get a bromo there. And that's one of the nice things about when we're doing bromination. We don't need to draw all of the products. We just need to draw the products that are relevant, the major product, because you're going to almost entirely get that major product. All right, so this section, and we're going to talk a little bit more about this later. Here we're going to be looking at halogenation as a synthesis tool, understanding how we can use the halogenation that we're talking about here in synthesis. So it's incredibly useful because you can take something that doesn't really have any functional groups. It just has carbons and hydrogens, and you can turn them into something that does have functionality. So as an example here, if we look at cyclohexane and we want to convert cyclohexane to cyclohexene, we have not had a way of doing that with the reactions that you had learned up before this chapter. So if we halogenate the cyclohexane to give us chlorocyclohexane, well, now we can take that and do an E2 elimination with a strong sterically hindered base like the potassium tert butoxide, and we'll get that new pi bond. And so that is an incredibly useful tool. We're going to take advantage of this kind of synthesis tool here. We're going to take advantage of that towards the end of the chapter. We're not going to do problems on it just yet because I want to go over a few more reactions before we do this. All right. I want to talk briefly about stereochemistry of halogenation reactions. Sometimes when we do a halogenation reaction, we will create a stereogenic center. So we may start off with something that's achiral and end up with a stereogenic center. But remember, and I've said this multiple times, anytime we have an achiral starting material, our product is either going to be achiral or racemic. So we will get either an achiral starting product or a racemic product. If you start off with a chiral starting material, then we have to look at, well, does the reaction occur at that stereogenic center? And if it does, we're going to get racemization at that stereogenic center. If the reaction does not occur, I did these sort of in opposite order. If the reaction does not occur at the stereogenic center, then the configuration at the original stereogenic center is retained. And so let me show you an example so it's not just words. All right, so let's start with an achiral starting material. So halogenation of butane. Butane has no stereogenic centers, so it is completely achiral. When we do halogenation of butane, we can get two products. We can get 1-chlorobutane and 2-chlorobutane. But if we want to look at stereoisomers, we'll see that 2-chlorobutane that has a stereogenic center, which means that we're going to get a pair of enantiomers. Because we're starting off, all right, so 1-chlorobutane has no stereogenic centers, and there's the 2-chlorobutane has a stereogenic center, but because we started off with an achiral starting material, we're going to have a racemic mixture of these enantiomers. So we will get a racemic mixture. All right, so to think about this, how this happens, we get the racemic mixture because the first propagation step, we're going to create a planar radical. This intermediate is also achiral. And so that means that this chlorine, which is going to come in and react with either, one lobe of the p orbital with the lone electron, or the other lobe, so it can either come in from the back or come in from the front. If it comes in from the back of this molecule, then we're going to get the chlorine in the back there, and we will get S2-chlorobutane. If it comes in from the front, we're going to get R2-chlorobutane. Well, it turns out the approach from either side is equal in energy, and so these are equally likely, and that's why we get a racemic mixture of these two enantiomers. So we will definitely get a 50-50 mixture. We have to. All right. If we do halogenation of a chiral starting material, then we need to take into consideration where is the halogenation occurring. So if we look at the compound 2-bromobutane, it turns out there's actually 4 different carbons you can do halogenation. You're going to get quite a mess of things here. But you potentially could do halogenation at carbon number 2, where the stereogenic center is. Well, if the reaction occurs at the stereogenic center, that means we're going to produce a planar achiral radical. We've lost that stereogenic center. Now that chlorine can either come in from the back or come in from the front, and if it comes in from the back, we're going to get one product, and if it comes in from the front, we're going to get the other product. So we'll take something that was achiral, but because the reaction occurred at the stereogenic center, we're going to get racemization of that stereogenic center, and we will end up with a racemic mixture of our two enantiomers. So, and that again, it's all because we got this planar achiral radical intermediate. Now, another place that the chlorination can occur, I mean, it can occur at carbon 1 and carbon 4. We're going to ignore those for now. We're going to look at chlorination at carbon 3. So if the chlorination occurs at carbon 3, well, carbon 3 is not a stereogenic center. So, but when we do the reaction, it will create a new stereogenic center. All right. Well, since carbon 2, that stereogenic center didn't get disrupted, its stereochemistry is going to be retained. The stereochemistry at carbon 3, though, we have this planar radical, and the chlorine can come in from the front or from the back. And when it does, if it comes in from the front, we'll get this one. And if it comes in from the back, we will get this one. Now, if you look at these, I'm going to encourage you to pause the video for a second and figure out what the configuration is. So bromine is carbon 2 and chlorine is carbon 3. Figure out what the RS configuration for each of those carbons is on this one. All right, now that you've had a chance to do that, this one is 2R, 3R, and this one is 2R, 3S. And again, you can convince yourself that that's true by looking at them. Well, our rules for stereoisomers, if we have multiple stereogenic centers, if the stereogenic centers are exactly opposite, then it's an enantiomer. If all the stereogenic centers are the same, then it's the same molecule. But if you have one stereogenic center that's the same and one that's different, it's a diastereomer. So these are diastereomers of each other. Now, would we get a 50-50 mixture of this? Probably not. And the reason is that when you have this radical intermediate, it itself is chiral, and so chlorination from the back versus the front are going to have slightly different energies. Which one is going to be lower in energy? I have no idea. But we probably wouldn't get an exact 50-50 mixture of these two diastereomers. All right. We want to look at the ozone layer and CFCs. CFCs are chlorofluorocarbons. But before we talk about CFCs, let's talk about ozone. Ozone, as you probably know, is it's elemental oxygen, but instead of 2 oxygens, it has 3 oxygens in the molecule. If you go into the upper atmosphere, into the stratosphere, this is where ozone synthesis will occur, is in that upper atmosphere. So oxygen molecules, as they're just floating around up there, will react with oxygen radicals. Now, these oxygen radicals are produced in a number of ways. However, one of the primary ways that they are produced is from this ozone decomposition. And this is a process where oxygen reacts with the oxygen radical, and we get ozone. It does give off a little bit of heat because it is exothermic. And then the ozone absorbs ultraviolet light. Okay, so it absorbs the ultraviolet light, and when it does, it produces O2, elemental oxygen, and these oxygen radicals. Well, the oxygen radical now can just react and produce a little bit of heat, and you'll get ozone again. So essentially, you're converting that ultraviolet radiation into some heat by doing this little trick. All right. Well, it turns out that absorbing of that ultraviolet radiation is pretty important. When it absorbs that ultraviolet radiation, that means that particular ultraviolet radiation does not get to the surface. There's just too much ozone up there. So this turns out to be very, very important. If that particular ultraviolet radiation, which is in sort of the deeper part of the UVC, if that reaches your skin, you will get sunburned, and that will greatly increase your risk of skin cancers. All right. And so this sort of steady concentration of ozone in our atmosphere makes it so that we are able to shield, the surface of the Earth from the ultraviolet, or at least part of the ultraviolet radiation, the ultraviolet C, that is particularly dangerous. Well, the reason that I mention this is that there are certain chemicals that can get into the upper atmosphere and disrupt this process. So we're going to look at chlorofluorocarbon decomposition. So CFCs are again, chlorofluorocarbons. And look at the properties of this. They are inert, so they don't react with other stuff. They're odorless, so they don't smell bad. They're non-toxic, so they don't kill you. And they're non-flammable, so they don't catch on fire or blow up. I mean, if you were looking at a property for a solvent or something, a refrigerant, something that you were going to put in your house, these are all great properties. They're almost ideal. And so they used to use them all the time as refrigerants, solvents, aerosols, all kinds of things. Some examples of some common CFCs are the trichlorofluoromethane, so CFCl3, and then this one, which has 2 fluoros and 2 chloros, so the dichlorodifluoromethane. And this is the CFC11 and CFC12, also called Freon 11 and Freon 12. Well, it turns out these molecules were extremely useful as refrigerants. You could take these things and put them into an air conditioning system, and they just worked really, really well as far as when you compress them, You compress them and and then it would generate some heat, but then you run a fan over it, and that causes it to cool down some. And then when you allow those the gases to expand, they cool down quite a bit, and you can use that in refrigeration. Okay, so great properties, perfect. However, sometimes Freon leaks. There's anytime you make a product where you've got a sealed container, you're going to get some of that Freon that's going to leak. And when that Freon gets into the upper atmosphere, it will decompose in the presence of ultraviolet radiation. It will decompose and give you chlorine radicals. Well, those chlorine radicals would react with ozone, and when they react with ozone, they create these ClO molecules, and those in turn would react with the oxygen radicals, and you would just get oxygen back. And then this would go back and react with another ozone molecule. Well, this means that to the extent that you have these chlorine radicals in the upper atmosphere, you're going to start catalytically destroying ozone. And that turns out to be a problem. So even a small amount of these can have a big impact on the amount of ozone. Well, that decomposition of the ozone led to what was called a hole in the ozone layer. It decreased the concentration of ozone in the upper atmosphere, in the stratosphere, and that led to increases of ultraviolet radiation getting to the surface and an increase in skin cancers. Well, these CFCs were used for much of the 20th century, and by the time you got to the 60s, the 1960s, this process was occurring at a significant rate, and then by the time you got to the 70s, it was a big problem. So scientists had to figure out alternatives. And the alternatives are hydrochlorofluorocarbons, which have a little bit different structure. You can also just use hydrofluorocarbons, but the hydrochlorofluorocarbons and the hydrofluorocarbons, they do something a little bit different. When these compounds, before they can even get to the upper atmosphere, before they can get to the stratosphere, they will react with the OH radicals that are present. And when they do, they will form this particular radical, and this particular radical doesn't do the same harm to ozone that the chlorine radicals do. And so as a consequence, these were less destructive to the ozone layer. Now, fortunately, in the 1970s, people started working on these and coming up with these alternatives. And by the time we got to the 1980s, there was real international pressure to solve this problem. And so in 1987, there was something called the Montreal Protocol, which was an international treaty where countries agreed to stop producing these, or at least cut down on these chlorofluorocarbons, and transition to some of these hydrochlorofluorocarbons and the hydrofluorocarbons. And here's the thing: it worked. So international community got together, and it helped. And so very slowly, the ozone layer depletion has receded, and now we're starting to get a little bit of regeneration of ozone in the stratosphere. So it's still not completely fixed, but it is projected by the late 21st century that much of the ozone hole in the ozone layer will be solved. Pretty cool. So a lot of people look at this and think, wow, this is amazing that international community can get together and solve a problem. It wasn't cheap. In fact, these are more expensive than your CFCs, but when it's a priority, they can fix it. And a lot of people have thought, well, maybe this is an approach we can take to solving global warming. And so far, that hasn't worked, but we can be hopeful. All right. Well, now we want to look at our next topic, which is looking at radical halogenation at an allylic carbon. Now, an allylic carbon is a carbon that is adjacent to a carbon-carbon double bond. It's not one of the carbons that's in a double bond. It's one that is adjacent. And if an allylic carbon has a hydrogen, which we'll just call an allylic hydrogen, if it has a hydrogen on it, then that carbon-carbon bond is much weaker than, or that carbon-hydrogen bond is much weaker than other carbon-hydrogen bonds. Just for an example, a primary carbon-hydrogen bond we saw earlier was at about 410 kilojoules per mole. Well, this one is at about 364, so it's much, much weaker. This is even more stable than a tertiary radical. So that's a big deal. So the bond enthalpy is weaker than even a tertiary carbon-hydrogen bond. So that allylic radicals are more stable than even tertiary radicals. So if we rewrite out our list, methyl radicals are still, much higher in energy, but the allylic radical is more stable than a tertiary radical. That means, particularly with bromination, we can do selective reactions at allylic radicals, and that's what we're going to be talking about in this section. All right, so allylic radicals, they are more stable because the pi bond can be delocalized, and we can draw resonance structures to indicate that delocalization. So here is the simplest allyl radical. It takes a little while to get good at drawing these, but it's really not too bad. And so we have this radical, we draw the resonance structure, and we put the radical on this other carbon. You'll notice that we don't end up with any radical character on carbon number 2, the middle carbon. Just like when we do this with carbocations and carbanions, we will get the radical at every other carbon. And so when we look at the hybrid structure of the allylic, we'll have a partial radical character on carbon 1 and partial radical character on carbon 2. All right, and we don't have it on carbon 3, and we don't have it on carbon 2. Okay, so number 40 is to draw some resonance structures. All right, so here we want to draw resonance structures for each radical, and I'm going to zoom in a little bit. All right, so there we go. We've got a radical, and we want to draw all the possible resonance structures. So we're going to start by taking this so we can clearly delocalize it around the ring here. We're going to take this, and we'll take the 1 electron. Again, remember to use your half-headed arrows. So it's like a fish hook. That one's not beautiful, but that's okay. And then we'll take this one and do the same thing going to that bond. And then we'll take the other half of this bond, and we'll go to this carbon. And when we do that, we've got a radical there. All right, I'm going to actually put the radical out here on the edge so it's consistent with the other one. All right, now let's do, we have one more possibility where we can take this radical and go there, and go there, and then this one can come to that carbon. And we have radical there. And if we did the hybrid, you'd see that we have partial radical character on every other carbon. So it's on this carbon, and this carbon. So it's every other carbon. And we're going to see that same pattern as we go through and look at some of these other ones. All right, so let's do this one. So we'll take that and go there, this and go here, and then this, we'll put that radical on that particular carbon. Now this one, when you're drawing this out, make sure that you leave a little bit of room down here because we're going to have two rows. We'll have two rows of resonance structures. All right, so now we have a double bond there and a radical that is here. All right, now we can't go any further around because this particular carbon is sp3 hybridized, and we won't be able to go any further. But we can go back into the ring. So we're going to do that. So we're going to kind of undo what we did previously. And we'll take this and go there. And then we'll take this one and go there, and this, and go to this carbon. All right, so we've got that, and then there is radical character right there. And I'm going to fix this particular double bond and make it look a little bit prettier. All right, it doesn't look beautiful, but so now we've got radical character there. Well, let's continue working our way around the ring. And I'm just going to put this one over here. All right, so we'll take this and go there, and one of these will go to that same bond, so we'll make a pi bond there, and then we'll take this one and go to that carbon. And when we do that, that'll be the same there. This one is still the same, but then we'll have radical here, and we'll have a pi bond there. All right, let's go to the next one. So here, there, and then we'll take this one, and it'll come out to this carbon. Again, if you're not sure, it's every other carbon. There, there, there. We've got radical here and a pi bond there. And this one's still sp3, so we haven't changed that one. Now we're going to take this one there, this to there, and this to that carbon. And at first glance, when you draw this one, you may think, well, that one looks just like this other one that we drew that was the starting one. But it isn't. It is a different resonance structure. And I will explain why. So there, and then we've got radical there and a bond here. And again, like at first glance, you think, oh, is this the same as this? It's not. If you look at the position of the pi bonds in the benzene ring, they're different. So this counts as a different resonance structure. We have one resonance structure left. And radical there. And that is all of our resonance structures for this particular molecule. All right. So we've got one more on this particular problem, and we can delocalize it here, and then this can come out to that carbon. That pi bond stayed where it was. We have a pi bond here, and now we've got a radical there. If you look, if you try to move around, this one to over here, you're going to find that you can't draw another resonance structure that has the same number of unpaired electrons. That's one of our rules for resonance structures. However many unpaired electrons you have on one, you have to have the same number on the other. And here, if we move it around, we're not going to have the same number of unpaired electrons. So so that's it. Those are the only two resonance structures for this particular one. All right. Well, let's go back to our presentation. And we want to look at allylic bromination with NBS. And you may be thinking, NBS, is that some sort of television network? Or no, NBS is N-bromosuccinimide. So N-bromosuccinimide. Because those allylic carbon-hydrogen bonds are so much weaker, it's possible to selectively do hydrogen abstraction at those in the presence of N-bromosuccinimide, NBS, we say for short, and either light or peroxides. So this is N-bromosuccinimide. Succinimide is, if you just take this bromine and put a hydrogen in place of that, that's succinimide. And then if you substitute it, it's called N-bromosuccinimide, so NBS. All right. So in the presence of NBS and either light or peroxides, a radical source, you can selectively do substitution at an allylic carbon. Pretty cool. So you can substitute those allylic hydrogens, and now you'll have an allylic halide, in this case, an allylic bromide. Now, in case you're wondering, can we do this with chlorine? Not really. It doesn't really work with chlorine. So you can do this with bromine. Remember, chlorine is a lot less selective, so the bromine seems to be our best choice here. All right, so allylic bromination, if we want to look at the mechanism for this, well, first we need to start with our initiation. Like, how do we get radicals to begin with? So initiation, we're going to start with the N-bromosuccinimide and either heat, or if you do it in the presence of peroxides, I think you can get it to work then as well. But our light here, light. And when you shine light on it, it causes that bond to break. You get this nitrogen radical. That nitrogen radical isn't that big of a deal, but the bromine radical definitely is a big deal. So that bromine radical can selectively abstract the allylic hydrogen and will produce an allylic radical. Now, with this allylic radical, it is resonance stabilized, so we will have some partial radical character on this other carbon. That becomes a big deal here in a minute. And then that will react with Br2. And you may be wondering, well, where did the Br2 come from? Well, it turns out it comes from N-bromosuccinimide as well. If you have the N-bromosuccinimide in solution, you can generate a little bit of, if you have a little bit of acid, like you do here, you can generate the Br2. And so that radical can now abstract a bromine from here, and we will end up with another bromine radical, which can go back and do step 2 again. So this is a propagation step. It happens over and over again. It's what we call a chain reaction. All right, so the allylic radical it reacts with a very low concentration of bromine. And again, I'll talk about where we can get that low concentration of bromine. It comes from the NBS. We'll talk about that here in a second. All right, so where does that bromine come from? Well, when you have that little bit of acid, the HBr that's formed in step 2, that HBr can react with another molecule of NBS. And when it does, it gives a very low concentration of Br2. Because the HBr is in such a low concentration, that means that this reaction happens relatively slowly. But we will get this reaction occur, and we will get that small amount of Br2. And that's how we get our low concentration of Br2. And you may be thinking, well, why not just use a high concentration of Br2? And I think you may already know the answer to that, right? You may already know the answer. If you go back and look, if you had a high concentration of Br2 with cyclohexene, you're not going to get allylic substitution. You're going to get dihalogenation addition across that carbon-carbon double bond. And we talked about that back in, well, first semester. I don't remember which chapter, but it's the addition chapter. All right, I paused and looked it up. We talked about addition reactions in chapter 10, so you can go back and review that if you would like. All right, so radical versus ionic bromination. If you have an alkene like cyclohexene and you don't have it in radical conditions, you have it with just bromine. Bromine will do addition. Remember the bridged bromonium ion? Again, go look at chapter 10 if you want to see that. And you'll get a transvicinal dihalide via the ionic intermediates. If you get the NBS with a little bit of light or peroxides, you will instead get allylic substitution, and you won't get addition, you'll get substitution. This is why we like to use the NBS, because it does give us that low concentration of Br2. Again, if we have the high concentration of Br2, we'd get this. We don't want that. We want allylic substitution. So, all right, so NBS and peroxides, that's the way to go. Or NBS and light. Either one will work. All right, and then again, the whole reason that NBS favors substitution over addition. All right, I had to fix a typo there. That was a really embarrassing typo. So why it favors substitution over the addition is that, if we have a low concentration, we're going to get the allylic substitution. Because that bromine is in such low concentration, it would have to react with a double bond to form the bridge bromonium ion, and then we'd have to have the anion come in. And so this is just that takes more time, and with the low concentration, we can avoid doing this. If the concentration of both the bromonium ion and the bromide are really low, then the overall rate of addition is going to be extremely low. So slow that you really don't get the addition reaction occurring. All right, so we want to look at regiochemistry of allylic halogenation. All right, and we'll often get a mixture of products. And that's because when we form the allylic radical, that allylic radical, as we've seen, has radical character on more than one carbon. And so here, when we do this particular reaction, we can abstract this hydrogen that is on carbon number 3, and we can get substitution of bromine on carbon 3, but we can also get substitution of bromine on carbon number 1. And the reason for this, we got to look at that resonance stabilized radical intermediate. Right, and so here is the radical that we form when we abstract. It's a allylic radical, and then that allylic radical will we have it resonance stabilized. If the bromine reacts with carbon 3, we end up getting the 3-bromo 3-methyl-but 1-ene, and if it reacts with carbon 1, we end up getting the 1-bromo 3-methyl-but 2-ene. All right, and we will look at number 42 as an example of doing this. So let's go back over here. And 42 is on both this page and the next page. There's 3 parts to it, so A, B, and C. All right, so here's how we want to start. First, let's draw the radical, and that's going to help you to determine what is going to be your products. So when we draw the radical, all right, we get the radical there that's at the allylic position of the cyclobutene. And if we draw the resonance structure for that, and I'm not going to draw the arrows, I'm just going to draw the resonance structure. So there is our resonance structure for it. Well, if you look at that carefully, this is the same intermediate as this. There's no difference between those two. And so that means that if you get substitution here, you're going to get the same product as if you get substitution there. So if we take this and we do the reaction, so we get our starting material, and we do the NBS, and we'll just do light, then we're going to get one product. All right. Now I say one product. Technically, yes, we're going to get, this is a new stereogenic center, so we would get more than one thing. Well, that's kind of ugly. Here, let me fix that. Well, that looks a little better. All right. So anyway, there is a stereogenic center there, but even though there's a stereogenic center, we're going to ignore stereochemistry on this particular problem. All right, let's look at this next one. So the next one, all right, we've got 3 different places where we can get a radical: here, there, and there. Again, we're going to ignore stereochemistry, and we're just going to look at constitutional isomers. All right. So if let's say we abstract, we're going to call this carbon 1. I'm going to go ahead and label this carbon 1, 2, 3, and 4 for identification purposes here. So let's say we abstract a hydrogen at carbon 1. So if we abstract a hydrogen at carbon 1, we'll get this radical, and we want to draw I just drew the same thing. We want to draw the resonance structure. And the resonance structure, we have that radical. All right, well, with those, we can get reaction here and here, and those are different. I'll draw the products here in just a moment. Now let's do the other possibility. What if we abstracted the hydrogen from carbon 4? All right, so if we abstract the hydrogen from carbon 4, we get that radical. And we get that as its resonance structure. So, and then these are different than these. And so we can get substitution in either carbon 1, 2, 3, or 4. Now, technically, if we were looking at stereoisomers, then we could also look at this particular one. It gets a little messy if we do that, but we're just going to stick with constitutional isomers. So if we get substitution here, we just replace that dot with a bromine, and that will give us the product. All right, same thing on this one. So put that bromine at carbon 3. All right, you get the, oh, not radical. We want the bromine there. All right, and then here we can put the bromine down there at carbon 4. And then finally, we could do the where the radical is at carbon 2, we'll put the bromine at carbon 2. All right, and so we have 4 different possibilities. Substitute at carbon 1, 2, 3, or 4. That one's kind of cool. All right, let's look at this last one, part C. And like I said, it ended up on the next page. There just wasn't a convenient way to do this. I'm going to put the radicals up here. So let's again number this, and as far as the numbering goes, we want to make that the lowest. So we'll do 1, 2, 3, 4, 5, and 6. And again, that's if you were naming it, you would call this the 1,2 alkene. Anyway, it's just so we can communicate about what is what. So let's say we abstract a hydrogen at carbon 3. So if we abstract the hydrogen at carbon 3, we get a radical there, and the resonance structure get the double bond there, we get a radical there. So that that resonance structure is definitely different than this. And then if we abstract a hydrogen at carbon 6, and then we could draw the resonance structure for that. Make sure that stays on the screen. We get the radical there. Now, if you look closely at these are identical. They're counted from different directions. So I'm going to put identical. And because those are identical, that means we're only going to get 3 products. So we'll get substitution at carbon 3. We can get substitution at carbon 1. And we can get substitution at carbon 6. And if we got it at carbon 2, then it would have been the same as carbon 6. So let's go ahead and draw what those products are. So NBS, and light, you can put peroxides as well. So if it's this one, once you have the radicals, it's super easy to draw what the substitution is going to be. You just draw everything, except instead of putting the dot, you put the halogen, you put the bromine. All right, here. We'll get that one. And then for our third one, we can pick either one. It's going to be the same. Oh, I meant to put bromine, not a radical. All right, and so we'll just pick this one, and we'll get bromine. And if you look, these are constitutional isomers of each other. Okay, so we're going to stop the video there. We're at almost an hour on this particular video, so we're going to stop it there, and we'll pick up on the next video. We'll pick up with oxidation of unsaturated lipids, so we'll look at that one.